So I'm going to do a modal analysis question, okay? And the question is a 2 degree of freedom problem, okay? X2. Okay, so there's the problem. Two degrees of freedom. We've got x1, x2. We've got a mass of m, mass of 3m. We've got k, 2k, and k. And in the question that I've given you some values, and I've let you off working out the first 3 steps. Okay, so K in this case is 120 newtons per meter. M is 2 kilograms. F1, we'll call that 5 cosine omega t. And F2 is 6 cosine omega t. So we've got sinusoidal inputs to both x1 and x2. Where omega is 3 radians per second. Now, like I said, I've given you the equation of motion. Okay, so we don't need to work that out, but you can do if you want to. So we've got 2, 0, 0, 6. x1 double dot, x2 double dot. In this question there's no damping, so we go straight to the stiffness matrix, which is 360 minus 240 minus 240 and then 360. And that's times by our displacements, x1, x2 equals 5 cosine omega t and 6 cosine omega t. Natural frequencies, like I said, are given to you. I've done steps 1, 2 and 3 of multiple degrees of freedom problems for you. 14 point, this is given in the question, 5482. Omega 2 is 5.3243 meters per second. And we've got the mode shapes, x1, Okay, so that's the question, and the question says, knowing these values, find the response of the system x1 and x2 using modal analysis. So we've done steps 1 to 3. They're given. Great, super duper. Step 4. Step 4 is modal masses. So M1, so this is using the equation on your equation sheet. You take x1 transposed times by m times by x1. One minus 0.2638 2006 1 And if you do the sums, like I said, the way to do it is to actually take these two terms first with your calculator. So I'll write out this one first. 1 minus 0.2638. And then you'll end up with a vector. These two multiply together. You've got 2 times 1. And you've got 6 times minus 0.2638. And if you do the sums, that should come out to be 2.4174. Okay, so like I said, you take those two matrices first, or that matrix and the vector, multiply them together, and you get 2 times 1, okay, and 6 times minus 0.2638. And then obviously here we've got 1 times 2 times 1 plus minus 0.2638 times by 6 times by minus 0.2638. And you'll end up with a value that comes out to be 2.41774. That's the first modal mass. So for the second modal mass, it's the same equation, except I've got the subscript 2 in here. And so we have 1.2638, 2006, 1.2638. And so you go through the same process and you get a solution this time of 11.5826. So there's M1 and there's M2. Oops. There's a 6 at the end of that term there. 11.5826. So step 5 is rescaling for unit modal mass. And the equations for that, we've got U 1 and so we take x1 and we divide each term by root 2.4174. And so we've got 1 divided by the square root of 2.4174. And we've got minus 0.2638 divided by the square root of 2.4174. So if you do the sums, you get 0.6432 and minus 0.1696 as U1. Okay, so you can see here's the same process for x2. Okay, you divide it by the square root of m2. m2 is 11.5826. So you take each value from x2 divided by the square root of m2, and then you get another vector. (0.2938) and 0.3713. So phi is basically those two things put together. Phi being the key to the relationship. So we've got U1 and U2. To deal with the applied forces. So the applied forces, you take the modal matrix and you transpose it. So that involves swapping these two numbers round. Okay, so that's swapped round there. Transpose. And then we've got our forcing vector here. And so this is going to end up as a vector. And we've got 0.6432 times by 5 minus 0.1696 times by 6, and that's all multiplied by cosine omega t. And at the bottom we've got 0.2938 times by 5 plus 0.3713 times by 6 cosine omega t. So step 7 is to find the modal equations. Now the modal equations will always be in the form of q I double dot plus omega I squared times by q I is big Q I. And in this case, big Qi is going to be, I'll call it F I times by cosine omega t. Now, this equation matches up very nicely with mx double dot plus kx equals f naught cosine omega t. M we can see is 1. K is omega I squared. F naught is fi. Okay, and we can also say that omega naught is omega I. Now we have the solution to this, because that's what we've just found earlier. And so we can, with the solution to this, we know is x is that. So therefore Q must be the same form. So Qi is going to be Fi divided by, we've got K is omega I squared, minus M is 1, so it's minus omega squared, cosine omega t minus cosine omega I t. Now from the solution we have Fi, or F1, sorry, is 2.1984. F2 is 3.6968. Omega 1 is 14.5482. Omega 2 is 5.3243 radians per second, and the forcing frequency is given to you as 3. So from this information, you can obviously plug these values into this equation for I equals 1 and I equals 2, and you get two values, two equations, one for Q1 and one for Q2. And those equations are Q1, if you do the sums, you get 0.01085 cosine of 3t minus cosine of 14.5482t. And Q2, again, if you do the sum, 0.19107 cosine of 3t minus cosine of 5.3243t. So that's step 7. And step 8, you have to convert it back to displacements. And the equation for that is given on the formula sheet. X is phi times by Q. We calculated phi earlier, 0.6432, 0.2938, minus 0.1696, and 0.3713. Square. Q1, Q2. Now at this point I don't expect you to write out these two equations in terms of these terms up here. Okay? I'm not expecting you to put these two terms into this and then write it all out in full. Okay? Because then it turns into a writing competition, not a dynamics competition. So it's acceptable to write x1 is 0.6432 times by q1 plus 0.2938 times by q2, and x2 1696 times by q1 plus 0.3713 q2. That is the solution to step 8.